Now we want to do a turbomachinery analysis with Ansys CFX. We want to design a centrifugal compressor with this data, inlet pressure 1 bar, outlet pressure be around 2 bar, um, the rotational speed RPM around 25,000, the mass flow rate around 3 gram per second, with 16 full blade, no splitter. The mass flow we need it for the boundary condition. The mass flow for each passage will be this value 1875 passage. To design this compressor, we can use Vista CCD just by drag and drop it here. We can rename it as first design. Open it. Our pressure ratio is 2 bar. The mass flow is 3 kilogram per second, and the rotational speed is 5,000. We can leave the other default value and just click calculate. We can see the meridional view the hub diameter. The shaft diameter at the hub is a little bit small. We can increase it by putting it at 5. And we decided to have no splitter and 16 blade. And we can check our efficiency. The efficiency for the design is good. We can accept this. Okay, close it, save it. Now, with our design, we must create a geometry-based design. If you right-click on the blade design and create a new blade gen, the geometry related to this design will be generated. Double-click on it and open it. Yes, this is our design. There are many features here on the blade gen. They are very useful. They are very important. We will talk about them in a separate video, but just as a quick review, we can talk about some of them. Each curve that you have here, or each value distribution that you have here, you can right click on them and convert the point to spline or Bezier, or you can change them as a piecewise linear or cubic spline. You can add more point on them, or delete some point, or combine some adjacent point. You can change the uh, value on the x-axis. For example, here for this is the thickness distribution at the hub. At the shroud is this one. You can click on this black circle here. This is the sections that are not black, means you cannot modify the data at this section to decide uh, which data you can change or you cannot change. Just click on the layer and decide about them. If you uh, click on this section, you can change, for example, angle distribution at this section. If you uncheck it, you cannot change it. Now, for thickness distribution, I want to change the thickness distribution at the mid span. Now I can change it. To change the thickness distribution, for example, at the hub, I can right click on it and increase the number of points by increasing this point as a 5 point. Now I can change it to the piecewise linear. I can change the location of this point by drag and dropping. Sometimes maybe I want to change in a specific direction. I can limit it to vertical or horizontal direction. Um, Here, for example, also I can change the meridional view by changing this point. This is our design, and we will talk about the specific feature of the software in the future. And this is the 3D view of our design. We can save it and close it. Now our geometry is ready to generate the mesh for Turbomachinery application. We can use TurboGrid just by right click on the blade and transfer data to a new TurboGrid. TurboGrid can generate the mesh only for components that have a vane or impeller inside them. For scroll, for volute, you cannot generate the mesh because there is no vane inside them. You can use another application, for example, ISM CFD for the scroll for mesh generation. Turbomesh, sorry, is a good, very good software for mesh generation for Turbomachinery application. I always prefer to combine the inlet and outlet of the geometry with the vane section just by clicking on the inlet and fully extended it for the inlet and for the outlet because you have a better mesh and you can define a tip clearance at the hub and at the shroud. For the hub is mainly for the stator and for the shroud is for the rotating. I will use normal distance and this value tip clearance. Now geometry is ready. We can generate the mesh with changing some parameter on the mesh data. But before mesh generation, we must unsuspend the topology. We can put the size factor as 1.3, the factor base as 2.9, and uh, our I think the best method for mesh generation is TurboGrid is using the Y plus method. I have an estimation of the Reynolds number in this geometry. It's around 1 e plus 6 plus 7, and you can verify this value on CFD post after your first simulation. In Turbomachinery application or in generally in the CFD simulations, the Y plus value must be around 5 to have a accurate simulation. We generate the mesh. We will generate the mesh for current settings by unsuspending the topology. We have the mesh, and we will see the y plus for this mesh. The y plus value is here. I forgot to talk about it. As we extended the inlet and the outlet, the software is telling that there is not any inlet and outlet domain, and just we can now the value for the y plus. Okay, we must use the y plus method. Now the y plus is around 40. To decrease the y plus, we can increase the expansion rate. Also, we can increase the factor ratio. Also, we can use size factor. I will put the size factor to 1.3, but the ratio around 1.33 is good. And the expansion rate to 1.6. Increasing the expansion rate will cause that we have not a good mesh, but we must decide about compromise between the high and low value for this parameter. Now the y plus is around 1.7. To check the quality of the mesh, we can see the quality of the mesh here. That there is a small number of veins, the mesh that are not good, which we can ignore it. Now our mesh is ready and we can save it. Now we can transfer our mesh to CFX. We have in the CFX, we must set up the simulation, we must solve it, and we must analyze the result. As I told you, in a separate videos, we will talk about each section, the advanced feature of each section. Uh, just now, I will tell you a brief description for each one. This is CFX pre. Can see the geometry, the mesh is here, and you must set up the problem. We have a turbo mode in the CFX, which is very useful. You can click it and choose the centrifugal compressor. Next, we have R1. We our the RPM is 25,000. The direction is not correct. It must be minus. We considered a tip clearance at the shroud, and now it's okay. The fluid is ideal gas, air, the reference pressure is 0, and we are using SSD and turbulence model. The best boundary condition for CFD for turbomachinery analysis is P total at inlet and mass flow at the outlet. P total at the inlet is 1, but as we decided the reference pressure be a 1 atmosphere, the this is the gauge pressure comparing to the reference pressure, therefore the P total at the inlet is 0, and the mass flow per passage is now we have we set up our problem. There are some advanced features for CFX3. We will talk about them in a separate video, but just you can increase the number of iterations by increasing this value. You can change the time scale. It's very important parameter here. You can decrease the residual targets and define some output control. For example, you can have some backup. For example, at each 100 iteration or for at each 1000 iteration, you can create a backup and keep all the backup. Also, you can monitor some parameter during the simulation. You can, for example, monitor the pressure at the outlet, pressure at the inlet, the mass flow rate at the inlet, the difference between the mass flow at the inlet and the outlet. For example, we want to monitor the total pressure at the outlet. We can create an expression here. Expression P total outlet. The function is mass flow average for variable total pressure stationary frame at location R1 outlet apply. Now you have the P total at the outlet and you can monitor it just by creating total total okay, and parameter for monitoring. You can create different expressions, different functions. We will talk about them in the future. You can initialize your domain. You can use the highest speed model. We will talk about all of this feature in another video. Save it. Now you can solve the setup by clicking on the solution based on the CPU that you have, based on the resource that you have. You can increase the number of the core by choosing the parallel simulation. For example, I will use 8 core for this simulation. You can initialize your simulation. We will talk about it in the future. You can increase the memory for this simulation. Now I can run. During the solution, we can monitor different parameters that we have defined in CFX3. For example, here this is the first iteration, second iteration. You can see the residual here. We have a user point here. This is the total pressure that we defined If you want to change this value, you can create a new parameter, for example, p total outlet. Okay, and choose a monitor point p total outlet, and you have it as a p total. And when the simulation finish, you can analyze the result. We will stop it now here. And you can use result for analyzing the result. We will talk about this in a separate video.